gentlemen, we are going to talk about a very specific protein today, and that is the protein function. Actually, not just a specific protein, a whole class of proteins, and really a function of proteins, and that is the function of an enzyme. So, if you don't know what an enzyme is, or if you don't remember from ninth grade, or if you've never been taught it before, here are your basics of an enzyme and the definitions that you need to know on these parts. So there are some really important components of it. I'm going to use the diagrams over here to talk about it. But an enzyme is actually a large molecule that's going to function to, like most commonly, a pair of scissors or a piece of tape. It's going to act on a little molecule called a substrate. It is either taking two substrates and putting them together or taking two substrates and ripping them apart at its most basic. There's a lot of other things that goes into it, but those are the two most basic parts of the actual just enzyme and its shape and what it looks like. The substrate, when it fits into the enzyme, fits in at a very specific spot called the active site. And that's going to be really important as we move forward and we talk about a couple things. Once those things bind together, it's called the enzyme substrate complex. That enzyme substrate complex is where the actual taping together or the breaking apart takes place and it happens. And then once it releases and it goes about its separate ways, then we go back to calling it the separate substrate parts and then the enzymatic or the enzyme, the components that are on there. An enzyme is also, in addition to being a protein, that's the class of macromolecules that it is a substance known as a catalyst. So a catalyst is something that's going to make a reaction happen faster. You can have other different catalysts in your body. 90% of the time, the catalyst is probably an enzyme because your body does not function, and this is true of all organisms, plants, wild animals, human beings. The rate of reaction in the body is not compatible with life. So to make life compatible, we have these things. There are these molecules called enzymes that speed up the rate of a reaction so that life is actually living and you can actually be alive and do things. Would you pause right now, see if you can't double check what are the bonds that are found in a carbohydrate, in a protein, and in a lipid? There is a bond name for all three of those. Hit pause, quiz yourself on that one. And then hopefully you remembered from the videos that we have watched already is that carbohydrate bond, the dehydration reaction, and that when it sticks that together and gets rid of the water right here between the glucose and the fructose is known as that glycosidic bond. Over here in the amino acids, when we pull those together, or a protein is the big class that's there. That is a peptide bond forming that polypeptide that is in there. Or over here in the case of the lipids, when we dehydrate the glycerol and the fatty acid together, we actually get the lipid molecule is all the way together. The one that it's showing you in here is the triglyceride. And the same thing happens on those other lipid molecules as they form various things. Remember the dehydration, hydrolysis, how those two things are done. So if you dehydrate something, you are getting water out of it. It's literally to be dehydrated, lacking in water, or hydrolysis, hydro, water, lysis, to split. You're shoving water back into something, you're rehydrating the molecule that is going to usually break it apart and split it into its two individual components. So enzymes can function in both of those ways. Enzymes can cause there to be these, we call them catabolic reactions, so when we break things down. So we're going to take the substrate, pop it in the active site. This is where it functions like a scissors, and it's going to pop those two molecules apart in the end. And you get your two products there. I like to think of it like this in the bottom. The simple A, B yields A plus B, and the enzyme is who has ripped those two things apart. That would be a hydrolysis style of reaction if the enzyme is most likely using water to shove those two pieces apart. It is adding that extra oxygen and hydroxide ion, OH, is adding a hydrogen ion onto the other side. From there, we have enzymes that function anabolically, or they build things up. This is when enzymes take monomers and turn them into polymers, or what I like to think of is they act like tape. So the substrate goes into that active site, you get the complex, and forever and ever, A and B are now stuck together. Generally, this has probably happened via some sort of dehydration reaction. So two things are now stuck together in there forever and always, and then water is a byproduct. It just goes out in there somewhere. A lot of things can happen. It's enzyme specific. So here are your two basic pieces. You can see on the catabolic reaction, there's probably energy that's given off by that breakdown that has happened. And then in the anabolic reaction to get things to stick together, so using the tape, we're actually adding that substance onto there. You can think of the tape as being the energy. So scissors, we've released little pieces that are in there, catabolic, anabolic, we have put a piece of tape on there. Make sure you know the difference between those two words. Come up with some fancy acronym that you can use, wordplay, so that you can remember the difference between catabolism and anabolism. What we're really talking about when we say that enzymes speed up the rate of reaction is this thing called activation energy. So it always takes us some sort of energy. Think of yourself like waking up in the morning. The alarm goes off, and then you have to actually like get up out of the bed and then get moving. It takes a lot sometimes, I know for myself, to like turn off the alarm and then like actually activate myself and like get up out of the bed and get moving. What an enzyme does is it lowers that activation energy. So it actually just makes it easier for you to like stand up and get out of the bed. It takes less energy to get yourself moving, to get going. So that's really what we're talking about when we say that enzymes speed up the rate of reaction, is they lower that activation energy, the energy required to like get things moving, get stuff happening on there. Just a bigger picture of the same graph. If you are a chemist and you have taken that and you really understand things, what we're doing is we're causing that delta G to just be smaller. So you can see that end product is a little bit lower. If we were without the enzyme, that rate of reaction, that hump in the reaction process, the amount of energy that's required is just so large. So delta G for these is just too big to be compatible with life. We want to lower that overall delta G, get that down so that life can proceed like it should. So it's all about Gibbs, all about that free energy. You thought you were done with that, but you are not. We also have another name for the way that the enzyme substrate like sticks together and they bind together, and we call it the induced fit model. Think of the enzyme substrate complex or the induced fit model a little bit more like a hug. So every substrate that fits into the enzyme, it looks a lot like a puzzle piece right now. Like, oh, look, that's a perfect spot. And this puzzle piece perfectly fits into there. True, yes, but it's a little softer than that. And so you can think of like, I like to think if I give my mom a hug, it's different than if I give another adult woman in my life, one of my mom's friends per se. It's still a hug. It works pretty well, but it's not quite right. So the enzyme substrate complex, when it does that complexing, that induced fit, also know and keep in mind that it's only one enzyme for every substrate. So it's only like every enzyme has one kid, and that's it. The whole world over, it can only work on that one very specific thing. It only hugs onto one molecule just right. There's lots of other ones that can fit in there and they'll be close enough. And so sometimes you can get like side enzyme product reactions and enzyme substrate complexes, but really and true, like moving, grooving, getting this thing to happen is because that right enzyme, that right substrate have bonded together, and then the action will take place off of there. So it's called the induced fit model. That's kind of how those pieces work in there. This is a real life example for you here is lactose intolerance. Lactose intolerance is actually that people who have this condition don't make enough of this enzyme called lactase. It exists in your small intestine. If you don't have enough lactase enzyme, when you consume substances that have a lot of lactose in them, remember lactose is milk sugar. So if you consume a lot of products that contain milk sugar in there, you can't break it down. Your body can't handle sucrose. It's actually not a substance for some people, the milk sugar version, not the table sugar version, but like lactose, the milk sugar version. Some people can't handle that, and so when it goes into their body, it can't break that properly, and so you actually can't absorb lactose. You have to absorb sucrose and fructose separately. If you try to absorb the whole thing really big, it doesn't get in there. People who have lactose intolerance, you know what that makes you feel like. You just feel bloated, you feel gassy because you're not digesting things properly, is what it comes down to. So the one in here that says sucrose, and then if you notice the enzyme says sucrase, it functions the exact same. There's another condition I could have used the same picture for, and it would have been, it's called sucrose isomalase deficiency, and it's literally you don't have sucrase, so you can't break down sucrose. So there's tons of different enzyme deficiencies in people. If you've ever heard of a baby having PKU or any human being having PKU, phenylketonuria, if you look on a can of Diet Coke, it will actually say on there contains phenylketonuria. Phenylketonuria is actually just an enzyme disorder. You don't make enough of a particular enzyme to break down a substance into a different substance. It's really cool. If you want to ask me questions on that one, just Google PKU. And then read about it. If you still have questions, then come see me. I think it's a fascinating enzyme disorder. I'm just giving you lactose intolerance here because it's a pretty easy common one you've probably heard of before. I like to think of this in terms of a graph and a chart. So in organisms, you can have lots and lots and lots of enzymes, and or you can have lots and lots and lots of substrates. So let's say you drank a whole lot of milk, then you have lots and lots and lots of substrates. Let's say that you are just stable in what you're at, you probably have lots and lots of enzymes ready to do work. Well, what happens when you have lots of enzymes and just some substrates, you can see over here in the graph, that rate of reaction can be really high. And so in this top case, you probably don't even notice that anything is happening because everything is working as it should. Flip that and have too many substrates and not enough enzymes, and this is kind of the disorder idea, there is a moment in time where it just levels off and your enzymes are maxed out, can't use those anymore. It's just not going to function the way that you need everything to function. This is where problems start to arise, and we get a couple of issues that are in there because we have maxed out those enzymes being able to do whatever the substrate needs them to do. There's a couple extra pieces that work on here. One of them is called a cofactor. Cofactors are additional little pieces that go into the enzyme in order to make it work. Some enzymes just don't work by themselves and they need a coenzyme. If you've ever heard of like vitamins that you have to take, some of those are functioning as cofactors. We're making sure that you have enough of them. Listed on the bottom are a couple of those: magnesium, manganese, iron, copper, calcium, cobalt. They're all cofactors. The enzyme needs the substrate plus that extra little molecule. Those are all elements that are in there in order for like the job to actually get done. Coenzyme is basically the same thing, but it's like a two enzyme sandwich that has to work together. You can't have one without the other. You need both of those enzymes to be together so that the substrate can have the action taken upon it. So sometimes it's just an element, sometimes there's an actual little enzyme that will pair with them. We call, no matter what it is, if an enzyme needs an additional helper, we call that helper a cofactor. The other side of this is that enzymes can also be stopped from working altogether. You can stop them from working in a non-specific way. So just, let's say you get really hot. Let's say that you have drank too much soda, so your pH is really high, or you are not feeling well, and maybe you're really basic, you've had too much milk, and you're not lactose intolerant, but like you just don't feel well. Well, you have lowered your overall pH, so you're really basic. Or alcohol does this as well. It inhibits enzymes from working. Heavy metals, this is how some poisonings work because you've stopped enzyme functioning from working. So there's a couple like non-specific ways that we can make these things happen. Those are some of the ways that we're going to play with, and we're going to take a look at some of those non-specific enzyme inhibitions. On the other side are very specific inhibitions that are there. And a lot of those work with one, your body is able to regulate them. And two, we can do that with a chemical or we can do that pharmaceutically. We can go in and we can actually block things from functioning or we can encourage them to work a little bit better. And it just depends on what is needed. Here's how they work. So essentially, be it specific or non-specific, what you're doing is you're taking the active site and you're breaking it. You're taking that functional protein and you are ripping that active site into some other shape than it used to have, so it can no longer accept the substrate. As long as you can get the substrate back at some point, like it can coil back up, we call it reversible, and we'll talk about those. If you've damaged it to the point where it is no longer able to come back, we call it an irreversible change. What an organism does is just disregards that enzyme and then it goes and it makes another one. So that's why you can get that function back. You can damage yourself for a little bit and then you can get it back. Some people don't have the right gene code, and we'll talk about gene codes later, in order to be able to get that back at some point. So how it works on temperature is that up to a certain point, enzymes work really, really well. And then at a certain point, high or low, that enzyme is just so denatured that it doesn't work anymore. With pH, how it works is basically the exact same way. Most enzymes work best in the human body between 6 and 8. Every organism has a different set. Different locations in your body have different sets. But essentially, it's the exact same idea that there's an optimal range, and you can see the two optimal ranges here. One is an enzyme that exists in your stomach. One is an enzyme that exists in the small intestines, and any organism that has a stomach and small intestine has these two enzymes. They exist, and there's two different enzymes in two different locations because those two enzymes over time, they have their optimal pH that they like, so they go to those two optimal locations to do their work and to do their job. And so it's a very coordinated, customized process all the way across. Competitive inhibition. This is going to be your first specific way that we are going to stop an enzyme from working. And that is literally we're going to go in and we're going to put something in the active site instead. Think of this like the goalie in a soccer game. We're going to literally put a goalie in front of that goal. That's a physical block to stop the ball from getting into the net. We're stopping the substrate from getting into the active site by literally physically putting a barrier in there. So this is kind of what it looks like from that molecular standpoint. If I give you all of the pieces, you can see in there that maltonate, if we put that in here, it goes in there. Physically, the succinate cannot get itself into that enzyme, so we can't break down that molecule. We can't rip the H's off of there. It's just physically blocked. Non-competitive inhibition works a little more like the defense. We're not putting anybody specifically into the goal to stop something from happening, but we are making it difficult. We're going to have people that come in, and this is where my analogy falls apart a little bit. When we stick somebody in there like the defense and they are working on the enzyme, the goal, how the defense actually does its job is it changes the shape, of that active site. So that non-competitive inhibitor that just went in there, it's not that they play defense and they don't move the molecule, they don't like move the goal, they don't make it harder for the substrate to get into there. They actually take the goal that should, look like this, and they might make it look like that. Or they might like depress it, or they might make it in some other shape so that that substrate can't get in there. So instead of being competitive, where we literally put a physical barrier in there, we're gonna stop you from working by not getting in your way, but we're gonna make your job impossible to do. An example of that one for realsies in life is cyanide. So cyanide is a metal. How that metal works is it goes in there and it goes to this enzyme, and we'll talk about what the heck that enzyme is in a couple units from now, but it goes in and it changes the active site of that number 4, and by changing that complex number 4, the flow of electrons can no longer happen. This is actually a picture of cellular respiration happening. It cuts off cellular respiration. If your cells can't respirate, you don't respirate, so then you done. That's actually how cyanide poisoning works. Feedback inhibition is going to work very similar to a positive feedback loop or a negative actually not a positive, a negative feedback loop. So it's going to only inhibit based on what is needed in the molecules that are around it. So if I don't need any more breakdown to happen, we're going to stop it non-competitively. If I do need that enzyme to be doing its job, I am not going to inhibit the enzyme from working. So if you think negative feedback, oh, I'm hot, I'll sweat and cool myself off. Oh, now I'm cold, I'll shiver and warm myself back up. This enzyme does the exact same thing. Oh, you need me to break down this threonine? Done. I'm happy to break down this threonine. Oh, we have lots of isoleucine now. We've done that. Okay, well, isoleucine actually goes in and non-competitively inhibits that enzyme from working. Stop. There's enough, no more, end of conversation. So it blocks that one. So negative feedback is how that guy works. There's another way cells can inhibit themselves. And then the last one is allosteric. So allosteric is kind of weird. It's kind of funky. It both starts and stops a reaction. It's a complex of enzymes that are working together. They require an activator to work. If the activator is present, then the enzyme will keep doing its job. If the activator is not present or there's an inhibitor in the way, then the active site is broken and it will not work. And it's just a quite complex way that enzymes can regulate their activity. And it's you need kind of a complex, you need 4 enzymes working together to make something happen. Remember, enzymes are a 1-to-1 type of ratio. Mostly they stay where they're supposed to stay. They can work with other people. We call that a multi-enzyme pathway. A lot of times they're working this way. They work in multi-enzyme pathways. They can do a 1-to-1 just by themselves, go out and work in there. But much like scientists, enzymes do like to work all together with people. Take a thought on this question, pause the video, maybe call a friend, see if you can't answer this particular question, see if there's something in there that you can kind of figure out, and then come up with some sort of answer, and we will talk about this on Monday the 29th. If you want to come ask me questions before then, you could come ask me questions before then, but hold on to that one because we will get to talking about that guy Monday the 29th with all of your questions. If you have anything, you need anything on enzymes, your book is a great resource. Crash Course has a great video. Amoeba Sisters has a great video as well. Let me know what else you need in terms of enzymes.